Thank you, Alessandro. The floor is yours.
Thank you, Carlos. Thanks to all the organizers for having me. Can you hear me all right?
Yes, loud and clear.
Okay, good. So, actually, I am not the head of the whole Fondazione Bruno Kessler. I'm only the director of the Research Center on Digital Industry. But as Carlos pointed out, we try to integrate research and the technology transfer in a virtuous loop. So the idea is to have our research implemented in concrete assets and solutions and apply it to technology transfer. And this is a cycle or a circle in the sense that the problems that we discover while doing technology transfer, for which we don't have a solution, become the theme of our future research. So I recently became director of the center, and the center comprises several units working on machine learning, vision, edge computing, formal verification, planning, so many different research topics. And we tried to encourage as an approach for the center the combination of techniques in order to achieve something beyond the single sectors. And predictive maintenance is one of the key areas of interest for the center. And I hope we will see why. So, of course, we know that the predictive maintenance is a thriving research area, but there is also a lot of interest in the in industry, and not only in large companies, but also for smaller companies, SMEs, and in particular, an initiative in Italy favor the ability to instrument machines and to basically provide the infrastructure for data gathering. So now we have many companies with large amounts of data available, and they have this idea that AI and deep learning will turn their data into useful information. And so there is a widespread interest on different application areas. Unfortunately, especially for SMEs, it's not really the case that you apply AI techniques, or in general, it's not really the case that you apply deep learning and then you'll get what you want. We'll see this in some of the cases that we are working on. Here are some of the examples, some example projects that we have been working on in the last couple of years. And as you can see, they are very scattered in some sense. We have been working on the predictive maintenance of tractors in the agricultural domain, processes for the fermentation of active principles in the pharmaceutical domains, the predictive maintenance of devices for the water depuration, the analysis of marine engines in private fleets, air conditioning plants, production of gearboxes, the operation of a hydraulic power station, and hollow glass production machinery, and also in the setting of robotic twin plant funded by the European Space Agency. So a typical example of such a project is the attempt to create an environment to collect, structure, and access data and training of AI solutions to classify user profiles and estimate the degree of calibration of electronic clutches the so-called kiss point in tractors. Okay, so basically, the idea is that these tractors are rented to farmers, and on one question is whether you can foresee and estimate what kind of usage has been done of the tractor, and this is because the single tractor can be rented multiple times. So you'd like to know that a particular part has been stressed a lot, and you'd like to rent the tractor to somebody who is going to use it for something different and stress other parts, so that the overall life of the system is increased. And the degree of calibration of the clutch instead is something that is very important to carry out a certain inversion maneuvers, like when from going forward, the tractor is commanded to go backwards. So the typical approach is that you collect data from the ECU, such as torque, the rotation velocity, the speed of the tractor, air and oil temperature, and so on. And you use deep learning algorithms trained on the available experimental data, and you estimate the degree of calibration. And depending on the difference between an expected value and you try to estimate whether the system is indeed calibrated properly or not. And the results that you obtain in such a project are based, are somewhat, let's say, mixed. We obtained very interesting results on one type of maneuver when the tractor is when the system was trained on the forward to backward maneuver, but the results on the forward, whoops, I'm sorry. The results on the forward to backward are the most accurate ones, while the forward to backward are less are acceptable but not outstanding. And here let's say the point is that it really depends on the application, what you whether this is acceptable or not. In this case, the point is that it is acceptable to have a reasonable percentage of a reasonable indicator in order to direct the activity of the human operator. So it like basically focuses the available human power on the specific activities, on the specific cases that are required. They require attention. In the general view, let's say general view that you see is that at the physical level, the machinery or the components are instrumented so that the data is collected, this data is transferred to the cloud, and then data analysis based on data mining, machine learning gives you the results, and then decision support system helps to decide when and where the predictive when and where the maintenance actions are required in order to optimize some functions. But in fact, I would like to say that this is a somewhat naive view in the cases that we have been exposed to, at least, or at least that doesn't cover the whole spectrum. So before I enter the challenges, I'm going to say that we are going to focus on the part related to the data collection and analysis, so the condition monitoring and diagnosis parts, and not focus on the decision support and the definition of good or optimal maintenance strategy that is out of the scope of this talk. I instead would like to talk on to focus on the challenges And so the first challenge is that this is really an interdisciplinary domain where many different aspects often need to be harmonized and integrated. A second issue that I find extremely interesting is that we often have a lot of background knowledge and that is available, for example, from the design documents or even the safety assessment documents. And we need a way to inject this background knowledge into the analytics. Otherwise, it is most likely the case that the data-driven AI, let's say the data-driven approaches are going to learn things that would be already known. So it's a challenge on how to represent and leverage this knowledge. Then there is another application, another issue that is very common in many application domains. That is, often you have families of products, and you'd like to be able to generalize from what you've learned of one product to other products that are most likely quite similar to each other. So it is important or even fundamental the ability to transfer knowledge or to be able to leverage what you've learned from one application to the next. And then there is a third, another challenge that is the fact that we need optimal or at least a good deployment on practical architectures. So here, as the dream or the let's say strategic vision on predictive maintenance would be to reach an integrated view and an harmonized view where 4 basic ingredients are combined into a unique framework and interact with each other. Of course, this framework would have to be tuned according to the specific problem at hand, but it would be much better than having to start from scratch for each application. So the 4 basic ingredients are organized as follows. The first 3 can be thought of as functional. So we have an issue related to advanced perception, meaning how do you transform the raw data into features. And as we will see, this is not a trivial matter. The second point is of course the set of techniques on that are data driven and rely on machine learning and deep learning. The third element is the whole set of symbolic techniques and models. So, if you will, formal methods to represent the background knowledge. And I think that the interaction between the second and the third is really in need of further exploration. It's definitely an important research challenge. The fourth element, the fourth ingredient is deals more with the physical architecture. It's no longer a physical, no longer a functional element, but it is related to the deployment, and it must take into account what happens when we go from the unlimited resources view to a situation where, due to practical constraints, you have a limited sampling rate, you have limited bandwidth and storage, computing power, and even energy, and so you cannot really collect everything as you would like. So let's go to the first ingredient, which, by the way, I'm no expert of, so bear with me for the if something is not completely accurate. But so the point is that most often the degradation status status can sometimes be observed, right? So, for example, in certain situations, you will see that an isolating barrier has decreased or has become too stiff. So you have to you can plan your maintenance based on what you observed. However, inspections may require time and cost and may block service. So a key problem is that but in general important features are not directly observable. And for example, bearing deterioration, you cannot open every bearing in order to see if what is its status. Okay, so vibrational signals collected by accelerometers may contain information on the actual degradation status. However, we may need advanced analysis here. In particular, we may need signal processing and statistical methods to detect nonlinear and non-stationary events that are related to fault evolution. And meaningful features are to be extracted from data using empirical modes decompositions, Hilbert-1 transforms, constant percentage bandwidth spectral analysis, and others. Of course, we can have symbolic models. So, for example, fault trees describing how the top level event of the bearing not working can be tracked to the for example, to the inner or the outer layers being compromised, or a certain number of balls being compromised, and so on. Okay. The interesting fact here is that depending on the analysis that you carry out, for example, here you see based on the frequency for a bearing that goes from normal condition to a fault that manifests into a break eventually. Here you see that it is quite hard to see where the fault is, but with different analysis, you can see also at very low frequencies that the fault evolution is perceived at in a much clearer way. Compare this view and this view. Okay, so the claim here is that depending on the components you are dealing with, you do need to have expertise in digital signal processing. As for the role of the background knowledge, the evaluation of a degradation based on time series analysis is not that straightforward unless you take into account, for example, the state of the machines controlling the apparatus, and also the integration of environmental conditions. So, for example, in the analysis of the track reversal maneuver, we didn't have the availability of the CPU, of the ECU signals. And therefore, we had to annotate manually the data to detect which phase was which. But consider, for example, the management of a train door, or the exploration rover power consumption. The raw data must be interpreted with the states of the controlling state machines. Clearly, if we know that a certain, for example, the door opening and the door closing are two different maneuvers, we should be able to use symbolic models to annotate the data. And this is basically saying that you need to process both the ECU information as well as the physical data. And similarly, the outside the conditions may be relevant here. So for example, if the temperature is much colder, then in this day, then it is possible that the opening and closing of the doors we require more time. So here I see a strong point for finite state machines in combination with raw data. The other important
Sorry to interrupt, Alessandro. We
yes,
are reaching the end of time. Are you close to the conclusions?
yeah, I'm pretty close.
Thanks.
Yeah. So another important application for formal methods is the idea of rule-based approaches that can be very helpful to express expected or unexpected conditions in response to specific events. Here I see a very strong connection with runtime verification, because if you can express rules symbolically, then you can compile them and use them to collect and annotate the data. The role of transfer learning, as I said, is extremely important because when you have trained a certain the classifier for a certain type A gearbox, you would like to know how to leverage this knowledge for a different type B gearbox. And this is one of the, as you can see in the marine engines, there are many variants of models that can that could leverage such similarities. The final point is that perception should not be thought of as something that is perfect. It should be done on edge, and therefore we'll have eventually to take into account the need of for this we will have to take into account these limitations. So the idea is that while the logical view takes into account sampling, feature extraction, and analysis, it would be important to understand how to map this on the actual edge of the network to limit the bandwidth, taking into account the limitation of the available nodes. And therefore, the idea is to have a virtualization from the thing to the cloud that will take into account all the possible architectural solutions. So here there are approaches in the formal methods world, in particular there is a tool set called the TASTE, where the physical architecture is modeled using AADL, and the mapping is automated. So design exploration makes it possible to analyze the deployment on different physical architectures, and possibly in automated manners is a problem of multi-objective optimization. So in conclusion, predictive maintenance is a very exciting domain because it requires interdisciplinarity, and many different aspects need to be harmonized and integrated, as we have seen at the functional level: advanced perception, representation of background knowledge, and advanced learning techniques, while the problem of automated deployment is very important at the physical level. I think that we are still far from a unified and adaptable framework, but this is what I think we are working on. So thanks for your attention, and I'll be happy to take questions.